Hello everyone. In this video we shall start with principles of stereochemistry. Before starting with principles of stereochemistry, we shall understand the isomerism. Isomers or the isomerism are when the two or more molecules having same molecular formula but their physical or chemical properties are different. When the two or more molecules having same molecular formula but their physical and chemical properties are different, these molecules are called as isomers, and the phenomenon is called as isomerism. And why there is a change in physical and chemical properties, even there the molecular formula is same? Because again the isomerism is divided into two parts to understand why there is a change in physical and chemical properties. And one is structural isomerism and the second one is stereoisomerism. Structural isomerism is also called as constitutional isomerism. Means here the molecular formula is same, but their structure is different. Because of the change in the structure, their physical and chemical properties are different. Means the structural isomers are the isomers which having same molecular formula but the structure is different. Means the constitutions of atoms is different, hence these are called as constitutional or the structural isomers. Again this is divided into many parts, and this part means the structural isomerism part I have discussed in the earlier video. I will give the link of that video in the description box. If you want, you can go through that video. And let's discuss about stereoisomerism. Here two or more molecules having same molecular formula and their structure is also same. Means the two or more molecules having same molecular formula and structure is also same, but what is the difference in that? Arrangement of atoms in space. Arrangement of atoms in the space is different. Means the spatial arrangement of atoms in the space is different. These type of isomers are called as stereoisomers. Means two or more molecules having same molecular formula, same constitution and sequence of covalent bonds, but differ in relative positions of their atoms or groups in the space. These type of isomers are called as stereoisomers. Again, the stereoisomers are divided into two parts. One is conformational isomers and the second one is configurational isomers. Then what about conformational isomers and configurational isomers? Conformational isomers are, these can be interconvertible. At RT. The conformational isomers are the having same molecular formula, but these can be interconvertible at room temperature. As because of the interconvertible at room temperature, these cannot be separated. These type of isomers are called as conformational isomers. And again, conformational isomers are divided into two parts: rotation about a single bond, and next one is amine inversion. This part means the conformation part is also I have discussed in the earlier video. Means there will be a Newman projections or projection, and there will be a restricted rotation about the cycles. In the cycloalkanes there will be restricted rotation, so that you are going to get a chair form and board form, all those things. Those are called conformers because of they come under the conformational isomers, hence these hence the chair form and board form are all called as conformers. Okay, then the next one is configurational isomers. Configurational isomers are, these cannot be interconvertible. Cannot interconvertible. The isomers which cannot be interconvertible. at room temperature, so that these can be separated. Okay, means two or more molecules having same molecular formula and structure, but these are isomers do not interconvertible rapidly at room temperature, and because of that these isomers can be separated. These are called as configurational isomers. Isomers is subdivided into two parts. One is geometrical isomerism and the another one is optical isomers. The geometrical isomers which have same groups in different positions around the double bond or cyclic ring, where there will be restricted rotation of atoms around the double bond or cyclic rings. Hence again this is subdivided into two parts, cis and trans. Cis isomers and trans isomers. This part means the isomers which have same groups in different positions around the double bonds or cyclic rings. This part also we are discussing in the earlier video, so if you want you can refer those videos. And next one is optical isomers. In this video we shall discuss about optical isomers. So first we shall understand what is optical isomerism. So the optical isomers are different from the other isomers because here two or more molecules having same molecular formula and the structure is also same and the physical and chemical properties also same, but their behavior towards a plane polarized light is different. Okay, see here how there is a change in the behavior of the lights towards a plane polarized light. Means here we have normal light. When the normal light propagates in all the directions, here you can see that the propagates in all the direction. When you pass this light through the polarizer makes it the plane polarized light. Means now the after passing through the plane polarized light, normal light becomes plane polarized light. Means it is propagating in a single direction. Now it is propagating in a single direction. When you pass this plane polarized light through the sample tube which is containing the sample, okay, after passing this tube there are two possibilities. Means there is a change in the plane polarized light after passing through this. Either it can rotate to the right or it can rotate to the left, or there will not be change in the direction of the plane polarizer. Here you can see that there is no change in the light after passing through sample, hence this is optically inactive. If the light changes, the direction of the light changes after passing through the sample, these type of samples are called as optically active, and it means that it's showing the optical activity. These isomers are called optical isomers. If the light is rotating after passing through the sample, light is rotating to the right side, this is rotating to the right side, these type of molecules are called as dextrorotatory. This is also optically active because this is rotating the sample. The light is rotating after passing through the sample. The light is rotating to the clockwise direction or to the right side, hence it is called as optically active. To the right side, hence it is called as dextrorotatory. It can be denoted by D or plus sign. And when the light rotates in the anti-clockwise direction or to the left side, then this is called as levorotatory. It can be shown by either by L or by negative sign. This is the optical isomerism. Means normal light propagates in all the direction. When you pass this normal light through a polarizer, you are going to get the plane polarized light which propagates in a single direction. When you pass this plane polarized light through the sample which is there in the sample tube, if the sample changes the direction of the plane polarized light, either to the right or to the left. This type is called as optically active. If the sample is not rotating the light in any directions, means there is no change in the light after passing through the sample, then the sample is called as optically inactive. Hence, if it is rotating to the right side, then it is called as dextrorotatory. It is denoted by D or plus sign. If the light is rotating to the left side or the anti-clockwise direction, it is called as levorotatory. It can be denoted by L or minus sign. Means sometimes if you have the mixture, if you are using the racemic mixture, means it is containing both dextrorotatory as well as levorotatory. Hence, half will rotate to the right, half will rotate to the left, then optical activity will be inactive, because half will rotate to the right because of the dextrorotatory, half will rotate to the left, hence totally it will be optically inactive. All the racemic mixtures are always optically inactive. This is about optical activity. Then how we can tell that? By looking at the molecule, how we can tell that this is optically active or it is optically inactive molecules? Means there are some rules or the criteria to be called as optically active compounds. Let's see the criteria for the optically active compounds. So the first criteria for the molecules to be called as optically active, or the molecule is showing optical activity, is molecule should be chiral. The molecule should be chiral, or there should be chiral object. Then what is mean by chiral? Chiral means non-identical mirror image. Means this is, I have taken the lactic acid. Here I will place the mirror. This is the mirror image of this lactic acid structure. Hence you can see that these are not identical. Let's see the structure. These are mirror images and these are not identical. Hence this molecule is called as chiral molecule. This is the first rule, that molecule should be chiral or it should be chiral object. This is the lactic acid structure and this is a mirror. This is the mirror image of this, and these are not identical. These are non-identical mirror images. Hence this is called as chiral. This type of molecule show the optical activity. Hence this molecule is optical active. This is the first rule for the optical activity. And see the some more examples. This is the structure of the molecule. When I place this mirror here, this is a mirror image of this. See this. This is below the plane, this is above the plane, and Cl is in the plane, CS3 is also in the plane. But rotate this structure, rotate this mirror image, so that Cl OH go behind the plane and H will come above the plane and Cl will be in the plane. When you rotate this, when you rotate the structure like this, Cl will be in the plane, CS3 will be in the plane, Cl also in the plane, but it is on this side. OH will be go to the back side, means below the plane. H comes above the plane. Now check these whether these mirror images are identical or not. Check this. H is here, H is below the plane, here OH is below the plane, OH is above the plane, here H is above the plane, so that these are non-identical. These are non-identical mirror images. Hence these are optically active. But let's see the other example. Here this molecule, I will place the mirror here. This is the mirror image of this. Here the CH2, Cl, CS3. This is CS3, CHH and Cl. When you rotate this, Cl comes here, this H goes behind the plane and this H comes above the plane. But check these two molecules, both are identical mirror image. These two are identical mirror images. Hence these are not chiral. These are These are not chiral. So the first criteria is the molecule should be chiral, means the molecules are should be non-identical mirror images, but here you can find the identical mirror images, hence this is optically inactive. Okay, these type of molecules are optically inactive. Next criteria is molecule should have chiral center. Molecule should have chiral center. The molecule should have at least one chiral center. Means you should know what is chiral center. Chiral center means we all know that carbon is the valency of carbon is 4, means the carbon is attached with 4 different groups. The chiral carbon is the chiral center should be the one which is attached with 4 different atoms. Here you can see the chiral carbon means sp3 carbon attached to 4 different carbons. Chiral center means, or the chiral carbon means, sp3 carbon attached to 4 different atoms. 4 different atoms. These are called as chiral carbons. See here in this structure, this carbon is attached to hydrogen, chlorine, bromine and CH3. Hence this is chiral carbon. We can denote it by asterisk. Here in the second case, this is chiral carbon. This is chiral center. Chiral center. Hence it is optically active. But here this carbon is attached to 2 methyl groups. Means same groups are attached to this carbon. Hence it is this carbon is not chiral carbon. Hence it is chiral carbon. No chiral carbon. Hence it is optically inactive. Means the 4 groups which are attached to carbon should be different. Here count the number of chiral carbons. Here one chiral carbon, this is CH3. There are 3 same groups are attached to this carbon, hence it is not a chiral carbon. This is also CH3. Here also there is no this carbon is not a chiral carbon. Here there are 2 hydrogens, hence 2 same groups are attached to this. But here this carbon atom, one is Cl, another is CH3, another is CH2. There is a 1 hydrogen group is there, hence all the 4 groups are different, hence this is chiral carbon. Like this you have to identify the chiral carbon. This is the chiral carbon which is attached to 4 different atoms. The count the number of chiral carbons here. This is not the chiral carbon, but this one which is attached to COOH, OH, H and this C. So that this is chiral carbon. Here also same. This carbon is attached to different atoms, so that this is also chiral carbon. There are 2 chiral carbons. And this is the second criteria, that is a molecule should have at least 1 chiral carbons. And the next one is molecule should not have any elements of symmetry. Means the molecule should not have any elements of symmetry, means it should not have any plane of symmetry, or center of symmetry. You should not have any plane of symmetry and center of symmetry. Means what is plane of symmetry? That imaginary plane along which the molecule can be divided into 2 equal halves. Means the plane is an imaginary plane along which the molecule can be divided into 2 equal halves. That plane is called as plane of symmetry. Here you can see that here you can have the imaginary plane. This is an imaginary plane. This is one half and this is the another half. These two are same. Hence this is having plane of symmetry. This is having plane of symmetry. This type of molecules are optically inactive. Means the molecules should not have any plane of symmetry, any elements of symmetry. Hence this is having plane of symmetry. Hence it is optically inactive. Again the second example. Here you can imagine the plane. Here you can imagine the plane. This is one part and this is another part. Both parts are same. Hence it is also having plane of symmetry. Hence it is also optically inactive because of the presence of plane of symmetry. Let's check the third example. Here you can imagine the plane. Here you can imagine the plane. but this part is different. In this part CS3 is above the plane, here in this part CS3 is below the plane, hence it is, there is no plane of symmetry, no plane of symmetry. Okay, and here also you can imagine the plane. Here to this carbon CS3 is attached, here Cl is attached, so it is not having any plane of symmetry. Both these compounds are not having any plane of symmetry, hence these are optically active. This is about the plane of symmetry. And next one is center of symmetry. Center of symmetry means atoms present in equal distance and in opposite direction from the center of the molecule. This is the center of the molecule. Check, this CS3 and this CS3 are in opposite direction, and these two are from the are in the equal distance. The distance from this to this is also same, and distance from this C to the center is also same. Here also the distance from the center to hydrogen and this hydrogen is same. So these two are same in opposite direction, these two distance are same in opposite direction. This molecule is called as, it is having center of symmetry, center of symmetry. So these type of molecules will not show the optical activity. These are the three criteria of the compounds to be called as optically active. One is it should be chiral, means it should be non-identical mirror images. And the next one is it should have chiral center, means the four groups which are attached to carbon should be different, means at least you should have one chiral center. And the next one is it should not have any planes of symmetry, and there should not be any elements of symmetry, means there should not be any plane of symmetry or the center of symmetry. If it having all these characters, then it's called, it will be called as optically active compound. Okay, thank you.